is about how human social networks evolve and change in time, on longer time scales, and on shorter time scales, how the individual interactions form the networks, and what consequences the time domain properties of such interactions have on the network structures. And now, this talk will touch upon the results of several papers involving several collaborators, people from Aalto, Laszlo Barabashi from Northeastern, and then several colleagues of mine from Oxford. So, what I'm going to be doing here is presenting some ways of how to take time into account when studying human networks of human social interactions. So, as a sort of a quick background, what's then the more traditional way of doing such analysis? Now, this is something that Renaud already pointed out. Typically, even when you would have detailed information about interactions between humans, like you do, for example, in mobile operator call databases, you just aggregate over them. You lose the time dimension by, for example, counting that me and Renaud were connected by 5 phone calls within a week or a month or so on. And that gives you static networks that you can also where you can also have link weights that are associated to each link. And if you have such things, then you can apply the sort of standard ideas of network science and study these entities. And for static networks, what do we know so far? If we consider social networks, especially from mobile telephone calls, we know that the tie strengths are linked to the network topology, such that high strength ties tend to cluster together to form groups, and such groups are then connected via weaker ties. So there are some correlations between tie strengths and network structure. We know that such networks are geographically and culturally embedded. For example, Renaud and others have studied a social network derived from Belgian call databases, and that network shows a great Belgian language divide, where basically people who speak Dutch don't speak with people who speak French, so the country is split, and that you see at the level of the network corresponding to an entire country. And such networks then affect a lot of things, the spreading of electronic viruses, the spreading of mobile viruses, you take into account mobility patterns, you get a better picture, and so on and so on. But that's more like the static picture, and what we want to do here is to take the time domain into account. So what do we have? Of course, there are many different time scales in such systems. If you consider the atoms of a temporal network of human interactions, you can think of them as the individual social interaction events. So that's the highest level of detail we have in the data, and also if you consider the human relationship between two humans, you can sort of decompose that into individual events of interactions. So that's the smallest, most detailed level. And then, if you consider a bit longer time scales, you have the dynamics of social ties. Some friendships and relationships grow in strength, wane in strength, fluctuate, and so on. So in network terms, this would be about changes in the weights of the links, or the strengths of ties. And then if you also go to other structural things, then you have dynamics of social groups, where the relationships between people change in time. And then you still go to higher levels, then you have some sort of dynamics that that's about the whole network, how the network grows, how the network shrinks, how the network underlying network topology changes or doesn't change in time. So for my first example, okay, before I go into that, one more thing. Here, one of the sort of key questions, which is pretty much a physics question, and also at the same time pretty much a social sciences question, is that how do these smallest scales translate into the larger scales? So how does structure on higher levels emerge from the details and the driving forces that take place on more detailed levels? And basically, this is you could actually define that this is what StatMech is all about, right? Statistical physics is about exactly this question. So what do we have? Let's first begin with an example that's more on the sort of longer time end of this scale, so medium to long time scales, and let us focus on how the networks around individuals change, how the link dynamics are. And for that, I participated in a study where we had longitudinal data on 30 students. So it's a small number of people, but what we had for them was all outgoing phone calls. So it's a large number of links in network terms. A small number of nodes, but a large number of links. And a long period of time, 18 months. And that data was collected during a time when these students went to university for their first year. So they finished high school, this was in the UK, they finished high school, went to university or had a gap year, but in any case were in a situation where their networks changed quite a bit, because people moved to another city, or if they didn't, their friends moved to another city. So people were in a setting where it was the likelihood of their networks changing a lot was very high. And then, because this was a small study, then we could augment that. We could augment the call records with some survey data. 3 surveys were conducted, where people were basically asked to list everyone they know, give their phone numbers, estimate some sort of an emotional closeness value, how close they feel to those people, indicate whether those are friends or family, and so on and so on. So, such that we knew something a bit more than simply that there is a link between people. We knew something about the nature of that time.
Sorry, what does longitudinal mean?
Time domain, so involving time. That you do that at several points in time. And then based on this data, what we did was to construct ego-centric networks. Now for network scientists, these are almost not like networks at all, because this is just a bunch of links around any person. So in ego-centric networks, it's simply me and everyone I know, and actually disregarding the links between the people I know, just links between me and the people I know. So in this case, basically what we have is a set of relationships, and because we are dealing with the sort of longer term dynamics of the system, what we did was we summed up all outgoing phone calls for 3 different 6-month windows, which we then in the end compared. So we know how many calls every participant made to their friends and family during these time periods, and this is then what we finally studied, how this pattern changes for each of the individuals. What you see is the following. If you take an individual, take the weights of links or link strengths to each of the alters of that individual, and you rank them by weight or by numbers of calls. And then you plot the fraction of calls going to those alters ranked you make some sort of a zip plot of the situation. Then typically what you see is something like this. Now this is a linear plot, so differences on the vertical scale are quite big. Mostly people communicate with one or two other people. A very big fraction of all outgoing calls goes to just one or two others. And the rest are not that. The numbers are far smaller. And this pattern is something that was there almost for everyone who participated in this study. And this is sort of the steepness of the decrease of this curve. This was, at least for me, was rather surprising in the beginning, because these are first-year university students. You would assume that they divide their sort of social capital more evenly among their friends. But no, usually it's such that one or two top acquaintances or friends or family members gets most of the time. So the pattern usually looks like this. It's broader than exponential, but it's not like a Paolo or anything like that either. Another thing that you see is if you monitor how the composition of these networks changes, its function of time, is that, yeah, it does change a lot. Now here, every symbol corresponds to when that friend was seen for the first time in the data, or if it's a family member, then we have a lila triangle. And what you see is when, for the second third of the study, for example, for this individual, most of the people in his or her network were newcomers. So old friends disappeared, and then new people emerged into the network of that individual, and he or she made phone calls basically mostly to new people, and then there were some top-ranking family members, even that person was quite close. And then if you follow this further on in time, even some more people appear, and some of the people who were lost for a time make a sort of re-entry into the system and so on. So there's a lot of change in the network of that individual. But what you always have is a shape that's still fairly similar. So the shape or how that person allocates his time to others remains rather similar. And actually, to such an extent that you sort of have something like a signature pattern for every individual in the study. For this person that's now depicted down here, this pattern is far more even. This is far more closer to the average of this set. Whereas for the top individual, the top two people or top one alters get even a far larger share of the traffic. And this is something that's remaining or is retained to a very surprising extent. And if you actually study this for everyone for these 3 6-month windows, you see that their pattern retains much of its shape, although almost everyone in the network changes. So what one can conclude from here is that for everyone there is sort of a typical way of carrying out or handling friendships. Some people allocate their time a bit more evenly to others. Some people always have one best friend or two best friends or things like that. And that seems to be, at least for the people in this study, that seems to be rather persistent. Of course, it may change later on in life, because now here the group, everyone in the group is a first-year university student, but at least for them they seem to have a characteristic pattern. But, okay, that much for the long time scales. We see that people's networks change, the dynamics, there are dynamics related to link strength around people, but there is some pattern that's still always there. So, but what happens then on much shorter time scales? And this leads us to the temporal network ideas that Renaud already mentioned. And to illustrate what really happens on the shorter time scales, I'll show you an animation that has all the phone calls and all the text messages sent between a couple of hundred people in a large data set during 1 month. Those are shown as flashing arrows, and as you shall see, there's a lot of time domain structure to this. So this is how the aggregated network corresponding to these phone calls or text messages would look like. Basically, it would look like a mess. You can't see much here. You see some green lines.
Depending from the students' studies.
This is different. So now I'm moving away from the student, starting to large-scale databases.
The questions to the student.
Yeah.
Could you find different types of people? Different communication?
Yes, absolutely. And basically, I could think that there are something like classes, yes. But as we have such a small number of people, it's hard to sort of statistically put them into categories. But basically, yes. And then the main differences are whether you are someone who sort of assigns or distributes or where the time allocation among your alters is close to the average or is more flat, or whether you are someone who basically has one best friend and that's all, and the rest don't really matter. So those are like the two extremes. And yes, you could probably sort of put people into classes or categories, but you would need to have a bit more data.
We could redo this in our game.
Brilliant idea.
Because we have hundreds of groups, which are your student classes, and once you enter,
yes,
once the group forms, you could redo exactly what
absolutely. Very good idea.
We'll do
that. Thank you. Beautiful. Nice. Okay, where was I? I was explaining that the mess that you see here is in fact a mess. So this is what you would get if you would aggregate over all communications by a number of people for 1 month. There is some network structure here, but basically it's hard to say very much about what you see in here. So this is a subset or subgraph, a small sample from a large call database. But then when you look at the calls, you see many things. So now every red arrow is a call, and there is structure that's there on quite a few time scales and also structural scales. So what can you see? First of all, you can see that the frequency is not even in time. There are periods of silence, and then there are periods of activity. Now this is very sort of, well, people sleep at night, basically. So this is not rocket science. There's a daily pattern to such activities. It's like a modulating curve over the entire system. Then some less trivial things that you see in the data is that often you have these sort of ping-pong patterns where A equals B equals A equals B, and there is a burst of activity between two people. Sometimes you also see chains of activity where A equals B equals C, even maybe D, within a short period of time. And such things basically are related to some sort of triggering or information transmission in the system. In any reference model, you wouldn't find such things happening. If the calls took place at random times, you would basically never see chains of 4 telephone calls. Sometimes you have patterns where A equals B equals C equals A again. So you have some non-trivial patterns in time that involve a big number of individuals. And then if you look at individuals, sometimes you can see even things that you could use to study or to understand the roles of individuals in the data. There are some nodes here that very frequently sort of initiate patterns. And there are some other nodes that mainly receive calls. And so you see something, you see things on a far more detailed level as you would if you would look only at the static network structure. So there's plenty of data in the time domain that you can use to understand the system. So, and this leads us to the concept of temporal network. Now, as I already mentioned, Renaud stole my slide, but I have a fancier version because I have this additional pink color here, so I'm better off. And here the idea is that you don't have, your networks do not have links that are permanently active. You can think that there's an underlying network, that nodes I and J are linked in the underlying network. However, that link is on. There's a connection between I and J only at very specific points in time. In this case, that would be a phone call. If any information is to be transmitted from I to J through this network of calls, then that can only happen when they actually call each other. So the times of the events matter a lot. And this is basically of importance to many things. First of all, you can understand the network structure by studying timings. Second, if you have any dynamics, from Renaud's random walks to things like simple spreading processes that run on top of such a network, then the timings are crucial for the outcome of such processes. And in a corresponding static network, you basically would miss a lot of things. For example, in this network here, if node A has at T0 a piece of information, and this piece of information is transmitted to other nodes at every time when there is an interaction, an event, a call between the different nodes, then only nodes A, B, and C would get the information within this window, because all the links between D and the rest take place at an earlier point in time. But if you aggregate over the observation period, you get a connected network. Every node is connected to all the other nodes. And basically, you are missing a lot about these dynamics then. So we don't want to deal with those, we want to deal with temporal things. Another illustration of many of the things that were sort of visible in this animation if you knew what to look for. Here I've plotted every phone call made by one individual within during 1 month. And those phone calls are the green lines, and then that has been subdivided into calls going to each of the neighboring nodes in that network of that individual, and those are the red barcode-like things. Now, if you look at either the green lines or the red lines, you see that this pattern is not uniform in time. You have the daily pattern and you have burstiness. It looks like a barcode. It doesn't look like just some random stripes plotted at uniformly random times. So there is burstiness, and that has certain effects that I'm going to discuss a bit later. You also see that this burstiness is really a feature of each social time. So instead of being a node level quantity that persons would actually act in a bursty manner, you see that the same sort of burstiness happening for each individual social time. Then, well, okay, the daily pattern is clearly there because you have these longer gaps at fairly regular intervals mixed with the burstiness. And then you can see the same thing that I already mentioned, that sometimes there seem to be correlations in the call trains in adjacent links. So there's some sort of triggering taking place. One call triggers another call. And if you look at these features with some more detail, then what does this burstiness in fact mean? Well, it means that the distributions of times between calls are broad. And there is a very big difference to a Poissonian reference. Poissonian is quite close to uniform in this case. I mean, if you, or even regular sequences, of course, if you look at long enough time intervals. When things are bursty, that means that you have far longer waiting times between events that were between calls than you would have if everything happened uniformly, randomly in time, giving in the end rise to a Poissonian distribution. You can see that if you rescale, basically if you had links of the same weight, where every link carried roughly the same number of calls, you would see that by calculating such quantities for the links and plotting the PDF of the inter-event times. But because we also have a broad weight distribution, I mean, as you saw, many links have a low number of calls, whereas some links have very high numbers of calls. You have to take that into account, and then you can plot rescaled inter-event time distributions, which then collapse on top of each other. That system looks like this. Your Poissonian reference would drop down quite a bit faster than that. But the shape of this is weird. I'm not going to go into any more details because I don't actually fully understand. No one fully understands the shape of this distribution. In the beginning, there is a non-scaling regime, and that's linked to something which is of interest, which is triggers, where basically we see if we take every outgoing call and calculate the time difference to every incoming call and simply do a count as function of these intervals, we see a peak at around 20 to 30 seconds, both for return calls and calls to new persons. So there is some clear triggering. A calls B and B calls C, normally after, say, 20 to 30 seconds. So there's a small, short response time. So there are correlated actions in this system.
Is that the typical time to dial for a phone?
That probably is, yes. That's what we figure.
Even if it is stored in the agenda, just by the time that you look at the
exactly.
At the Poisson call. Yeah.
This is what I think it mostly is. That you have to, someone calls you, you immediately want to call someone else, and then you just have to go into the contact list or number list and make that call, and that gives rise. So this is sort of this peak is not of a very fundamental nature. You see that technology is like this.
And what about the duration? Why
12 hours, usually at night. So that's again the daily pattern. That
independently of when is the reception of the call?
But receptions are also mainly at daytime. So that comes from the fact that nights are basically silent. And then there's something which has a power law-ish slope in between, which I don't understand that well. Okay, so there's triggering, and then there is a daily pattern. And if you plot the network level call frequency as function of time, then this is how it typically looks like. This is how it looks like for our data. This is how it looks like for many other data sets from some other countries. At night time, very low number of calls, then you have a peak around lunch hour, and then you have another peak in the early evening. And then actually weekdays are different. The call levels are smaller in the weekends on Sundays, whereas Friday nights are then call activities very heavy. So there are these different time scales at play here. But okay, so we have such things modifying the timings of events or calls in the network. Now suppose we have some process running on top of that, like Renaud's random walks, or something which is much more simple than that, a spreading process where initially you infect one node, say with information or anything, and then at every phone call that person makes, the neighbors are infected, and then at every phone call they make, they infect their neighbors. So it's like a light cone of information spreading at maximum velocity in this system. That there's 100% transmissibility for transmission probability is 100% for this piece of information, and it always picks the next phone call it can spread on. So we can put such spreading dynamics and play on top of the call sequence, and then we see something happening. Now, if we want to understand that something a bit better, then we have to resort to what Renaud also mentioned, which is different null models, where you have destroyed some of the time domain correlations. But simply to first have a look at what happens here. This is again real data. Now, this person was set to infect this state in the very beginning. And every phone call between red and white nose makes the white nose red, transmits the infection. And this is what you see. The process is actually, it looks fairly slow because of several things. Because of temporal correlations, because of the ping pong patterns, and actually what you see here is that even after a fairly long time, not every node in the subsystem got infected. Again, if you would have a static network and you would model the spreading process, in the outcome everyone would have gotten the information. So there are differences to the static case. And then if you run this process using big data, using how many phone calls did we have? 300 million phone calls or something like that. And then you get curves that looks like this, the red one in here, which look more or less like epidemic spreading curves look like. There is an S shape, where the spreading lifts off at some point and then saturates, in this case at 100% because we are repeating the sequence. Now, if you then
do different curves,
explanation is coming. So the different explanations are different null models. And I won't have time to go into the technical details of those different null models, but basically those are reference models where you modify the time sequences somehow, such that you destroy some of the correlations I mentioned. For example, you can destroy all the time domain correlations with the exception of the daily pattern by taking the timestamps of every call and switching them randomly. You have the same numbers of calls between the same people, and the overall call frequency in the system is the same as you had, but you lose triggers, and you lose burstiness, and you lose things like that. Or you can have more fancy versions of that, where you take call sequences of individual links and shuffle them around using some rules to get rid of some of the time domain correlations. The outcome here is that whatever you do, basically your original data is slowest for any spreading process. And in this case, this mainly comes from the burstiness factor, that if links are bursty, it slows down any dynamical process. This is very easy to understand. Now, suppose that the piece of information arrives at me at a random point in time, and when I next time call a friend of mine, I'll immediately transfer that piece of information. If I call my friend 7 times a week, such that I call him or her every day, then on average the information will be transmitted fairly quickly to that person. If I make those 7 calls on Friday morning, and then for the rest of the week the link is silent, then you have longer waiting times. And this is exactly what burstiness is, that events are close to each other. There's a bursty train, and that makes things slower. For reasons that we don't fully understand yet, even the triggering correlations and other temporal correlations don't seem to act in a way to sort of counter this enough. There is not much difference in a null model where you remove the triggerings and the original case. But nevertheless, the differences between the different null models and the original are fairly large. And this speaks in favor of always using time domain information in such modeling if you have it available, because the outcome will be greatly different from any static assumption where basically you are removing all of these different correlations. Okay, then to my final topic, or final aspect here, a couple of slides about temporal patterns. Now, as I mentioned, in the data you sometimes, or in this animation, you sometimes see things where A equals B equals C equals A, or A equals B and then B equals 10 people. Not times 5, or something like that. So there's a pattern that somehow represents flow of information in the system. And it of course would be very nice to detect such patterns. How frequent are they? What sort of patterns we have in the system? How significant those patterns are. And for that we did some work and developed a framework related to temporal motifs in the system. Now in static networks, motifs are basically just frequently occurring subgraphs of certain shapes. But we want to do the same in the time domain, such that we find out patterns where links activate within a short time period. And for that, you can define temporal subgraphs as sets of delta T connected events or calls or interactions, where the delta T connection means that the events take place within, they succeed one another within a period shorter than your delta T. So this delta T is always a parameter in your system. Using that, you can define and count temporal subgraphs in your data, and then by removing the exact timings of such subgraphs and just considering the order of events, you can then come up with equivalence classes, where basically this one would be that A equals B, A equals C, then B equals C, without worrying about the exact times of those calls. And then you can do some clever tricks, which I'll skip. If you are interested, you can check out this JStatNet paper, or the archive version, where you map such temporal subgraphs of ordered events into directed colored graphs, and then use any of the existing ways of detecting graph isomorphism. And then what you get is you do that, you write the software, you input data. What you get is you get a count of things, count of temporal animals in your data, the count of all possible patterns that look like all possible temporal patterns in your data. Now, the problem here is that this is a big zoo of animals, basically. You have plenty of animals, you have a lot of different things that can happen in your data, and unlike with static motifs where you have reasonably good reference models that allow you for assessing the significance of some patterns, for temporal networks, this is the hard part, because basically any of these time shuffling things destroys all of this. So every reference model where I start switching timestamps around, and then I do this count, it's close to 0 for every animal. So assessing statistical significance is hard because it's very high for every pattern using normal models. But basically what you can do is you can compare the numbers, you can compare the order, appearance order of different subgraphs or motifs like that. What you see here is that the most common things are just these ping-pong patterns. A equals, B equals, B equals, A equals, and so on. Because it is basically that's what such a temporal network mainly does. People mainly call each other repeatedly, and the other patterns are more rare than that. You also see that the least common motifs are things which you can think of that they are not causal sequences. In that, for example, you have things where A equals B, then C equals A, and then B equals C. Within that sequence, those things cannot have caused each other, and that's why it's fairly infrequent. And this also speaks in favor of sort of interpreting the higher frequency motifs as signatures of some sort of information transmission in the system. You may also see things relating to different user groups. For example, that if you take all the females in the data, compare them to all the males in the data, and compare different motifs, you see some rank order differences. That for females, motifs where people communicate in triangles are more frequent than they are for males. For males, some other types of motifs are more important. However, this may relate also to the numbers of people in these different classes. So more work on the null models will be required in order to fully understand this. But basically, what I would expect is that if you consider age groups or gender or things like that, you should see different behavioral patterns and different motifs in the data. But we are not there yet. So this is basically sort of work in progress. Designing proper null models is a very hard task, and this is what we are doing at the moment. So more work will be needed to fully understand the significance of different patterns. And I guess this is where I'll finish. And then, if you are interested in any of these results or any of these topics, here's a list of papers by our group that you can find online. Thank you.
Thank you, Jari. Questions, comments? Yes. Do you think any of the results you have found can be understood with some kind of waiting time? So for the approach by Renaud before? Is there any...
Those are definitely linked. So I hope so, yes.
But not yet established?
Yeah, there's much to do. And I think one of the things that is hard, at least initially hard to incorporate into these analytical things, is correlations between the waiting time or the sequences of adjacent links or larger entities. So that's hard it's hard to actually even measure. I showed you some things, and we know that there is this network level pattern. We know that causal links sometimes trigger other things. I saw that we showed that we have these motifs and so on, but there are correlations of many different kinds and orders in the networks, and taking those analytically into account will be challenging. But I'm glad that Renaud will have a lot of work to do in the future.
Jari, you started saying that would be an empirical talk, and most of what you showed us is how to classify or understand the data. And you ended up saying, well, we need to work out some null models. So,
yeah.
On the theory side, what should we expect? Or at least, I mean, what are the questions that from a theoretical point of view one would like to address after having classified or analyzed this data?
Okay, one of the questions that is sort of still open is that if you take, for example, the simplest process of SI spreading, where something always infects neighboring nodes, which is like the light cone for any dynamics. That's the fastest dynamics that can happen on your system. Every time there is an action, something is transmitted. Now, for this network, what we see is that you have burstiness, and that slows things down. Whereas there are results by Petterholm and others for another data which is related to sexually transmitted diseases, where you see sort of the opposite, that actually the time domain correlations in the data speed things up. You remove those, things become slower. In this case, it's the opposite. So, under what conditions do the time domain correlations in a system speed up or slow down different processes? And then if you go to the theory side, if you go to things like SIR, where in addition you have the normal percolation problem. In this case, you always infect the network. If you have SIR, you have the percolation problem, that depending on the parameters, you infect the system or your disease dies out. You plug in these time domain things, what do you get? Even for toy networks, I mean for the normal network models, if you say you take everything, your Parabashi algorithm or whatever, you assume certain types of inter-event sequences on the links. and you plug in SIR, what do you get? What's the outcome? So I think there's plenty of things to do in that respect.
Okay. Yes, please.
What is the time step for all these data?
See?
What is the time step?
What is the time step?
Yes.
I mean, these are the last part of the talk was about records from the billing system of a mobile operator. So every time that I call someone, the system records that at 12:06 Jari called Renaud, and that call lasted for 45 seconds. And those are the timestamps. We have access to that database, so that for anonymized individuals we know the times.
When you say the call occurs at time 1, time 2, and so on, that's how you use some sort of average this, or
No.
maybe in some period, or
no. Let me show you the one picture. For example, in this picture. Now we know every phone call with an accuracy of 1 second,
okay.
and that's the timestamp.
Oh, 1 second.
Yeah.
That's okay.
More questions or comments? Yes. Stefan.
Your curves, where you showed the time, the information spreading thing.
Yeah.
These are logistic curves, or do you see somehow the network in these? Are these purely logistic?
Logistic in shape, you mean? I
Yes.
mean because I mean, for most of the networks, curves would look like this, unless you have something with a very broad degree distribution where this lifts off very quickly.
But have you tested? Are these logistic or?
We haven't tried to fit any functional form into it, with the exception of trying to fit an exponential in the beginning of the data. Because I mean, if you have mean field SI or SIR, you have an exponential growth in the beginning. Here you don't have it. Here you have something which doesn't really fit exponential very well. And please don't ask me why, because we don't get it. Most likely, it's the different temporal interplay of the different temporal correlations with the network topology, because you have communities and you have weak links connecting the different communities that act as bottlenecks. So that makes the spreading slower in the beginning, and then it sort of explodes at some point.
But it would be interesting if you just see a logistic curve, meaning an exponential curve at the beginning and then a finite size. Or if it is something more complicated where you see all these network features.
And of course, I mean, this is an ensemble average. And if you look at individual curves, you have plenty of there should be a paper in the archive this week where we actually studied such details a bit better. So for individual networks, you see a lot of variation. And then if you would zoom in here into the very beginning, you even see sort of the daily pattern, the community structure, things like that, at the very smallest level of detail.
Yes, Igor.
How far are the information propagation information really here representative? Because it certainly neglects all other kinds of channels.
Absolutely.
Spread, right?
Absolutely. So what this basically is a sort of tunable probe on the maximum velocity of information spreading on top of this particular network. So it's rather far from real world at this point still. So of course in the real world you would have all the different channels, and you would never have a spreading process which sort of goes through the entire network just like this. For most things don't spread. In every viral article experiment, I mean, you can have small clusters of tens of people, maybe hundreds, but you never get a regulated spread. So that would be. There are different channels, and nothing is this contagious in the real world.
Nothing else? Then thanks again, Jari.
It was very interesting.